All right, Chapter 8 talks about logarithms and exponential functions, and as it pertains to calculus. And so we're going to be doing derivatives on logs and exponential functions and things like that. And so at the beginning of Chapter 8, we do a little bit of a review and preview. There's some basic things that you need to remember how to do. And so let me just get the text up here for you. Okay, so just some basic refresher here on exponent laws. If you have the same base, two terms with the same base, and they have different exponents, you keep the base and add the exponents. Right? The quotient law here is again same base. If you're dividing, you subtract the exponents, top minus the bottom exponent. If it's a power raised to a power, then you multiply. If you have a product raised to a power, then each term each factor inside the exponent applies to. All right. If you have a fraction or a rational taken to an exponent, that's the same thing again as this one up here, except this exponent applies to all factors in the numerator and all factors in the denominator as well. A to the power of 0 equals 1, or any base to the power of 0 equals 1, unless that base is 0 itself. Of course, that doesn't work. And if we have a to the negative r exponent, that's the same as 1 over a to the positive r exponent. So the exponent laws here, these you should have familiarity with. All right, well, let's talk about logarithms. So logarithms, as you learned in pre-calculus 30, logarithms are a response to solving for a variable, basically, that's in the exponent position. And so in order to talk about logarithms, we first need to refresh ourselves, I think, on exponential functions. Okay. So an exponential function would be y equals b to the power of x. So an exponential function is where literally the x value is in the exponent position. Okay, so the independent variable there, the input variable, the x, is in the exponent position. That's an exponential function. It's different than x squared, right? It's not a variable taken to a number exponent. It's when the actual variable is the exponent. And so what we did in pre-calculus 30 was we explored the graphs of these, which we will real briefly here again. But when we tried to solve for x, right? How do we solve for x? How do we get the x out of the exponent position? And that's where we try to identify what's the opposite operation for taking a number to the power of a variable. How do you undo that, right? And that's where we came to the idea of logarithms. So the logarithm, and it's in your textbook here as well. We'll just maybe pop over there. In your textbook, it says, I'm just going to zip a little bit here. There we go. Okay. The logarithm is the exponent to which the base b must be raised to give x. Now they use x and y and b here a little bit differently than I am, but let's just go back. So this exponent really can be expressed as a logarithm. And I don't know if you guys remember this, but the logarithmic statement and the exponential statement are related. And so this is how they're related. See if you remember this. Okay? So the log of x, base b equals, sorry, I'm using this terminology, it's the log of y. Base b is x. So the log of y, base b, equals x. Yeah, because I'm going to put x up here. So what that means is when you look at these two things and you're looking at this way of writing it, and this logarithmic way of writing it. You look at b as the base here, which makes sense in the log, right? This is the position for the base, and that's going to be some number like 2 or 10, 3 or something like that. And the base is taken to some power here to give you y. So the base to some power gives you y. That's how I kind of like reading it. The base to this power equals y. Okay? Or y is this base to this power. So if we do some actual kind of real life examples here, let's say 25 is 5 squared. All right? So if we write this in logarithmic form, what's the base here in this expression? If we've got a power, what's the base? Yeah, the power is over here, the base is 5. So 5 goes in the base position. Okay? The logarithm of 25. 25 goes here, and then 2 is the answer. So what the result of this log is the exponent. That's how we can solve for x. See, the exponent is the log of this number with this base. Okay? So what is the log of 1,000 base 10? What's that? Okay, so you ask yourself, 10 to what power equals 1,000, right? 10's the base. The answer is 3 because of that. All right? And what's the log of 32 base 2? So the log of 32 base 2. So you're saying if I were to rewrite 32 as a power and 2 is my base, what would be the exponent part? And yeah, that would be 5 because 2 to the 5 equals 32. Is this making sense? Is this refreshing your memory here at all? Okay. All right. So I apologize. I'm using a little bit. The letters and numbers are maybe a little bit different than the book here. They've got x and y switched, so that's what threw me off there before. But it doesn't matter. As long as you think of base as this is the base in the exponential form, and this is the base right here in the log form. Okay. Properties of logarithms. Go back to your textbook here. Where were the properties? Okay. Some questions for you. Laws or properties of logarithms. Okay. So these ones here look like they're on page 353 in your text. Okay. If we have two numbers and they're positive numbers for now. Okay, we're going to say they're both positive numbers. And if you have a log of some number that can be split up into two factors, you can also split that log into two different expressions. So log of x times y can be written as the sum of log of x with the same base plus log of y with the same base. So what that means is, as an example, the log of, let's say 20 base 3 can be written as the log of 5 base 3 plus the log of what? Base 3. What would go there then? Or is the factor that goes with 5 to make 20. Right? And we'll just do this, maybe do this once, but if you get your calculator out, and you do that on your calculator. So find your log button on your calculator. Now, I have to mention this. This log button right here is actually going to be log base 10. It's called the common logarithm, if you remember. So log base 3, you may or may not be able to do this on your calculator. To tell you the truth, I haven't kind of gone this far. I wasn't going to do this. So let's just see. I don't think it's anywhere here. So you'd have to do this a little differently on this calculator. But for those of you that have a calculator where you can put a separate base in there, does anyone have a calculator like that? I do, but not on my screen here. Right? So, anybody? No? Alright. Well, I do. I have a calculator off the screen here that I will use. And log of 20 base 3, let me just put that in. Alright, so my calculator gives me 2.72 as the value for this. So what does this mean? What does this statement mean? That equals this. How do we write that in exponential form? Three is the base. What's the power? About 2.7268 and so on. I've got a big decimal here. Is going to equal then what? Should equal 20. Yes. Okay, see? Base to the exponent equals this part right here. So, if you do this on your calculator, all of you can do that. Let's just check that. Okay, let's just check that. And you go 3 to the power of, we'll use as many decimal places as we can here, 68 equals, yeah, 19.999. So that's pretty much 2. If we used all the decimals, we would have got 20. All right. So, again, so you guys can't do this maybe on your calculator. And there probably is a way on the graphing calculator. I just don't know offhand how to do that. So log of 5 base 3, let me just do that for you. Is 1.46 or so and change. And this one is 1.26 and a little bit. So that's going to be 2.6 or 2.72. That's what that is right there. Okay. So you see how this property works for this example. You see that? And like I say, we could do a whole bunch of confirmations, but we won't. If you have a division, you could also express it as a difference of logs. And this one here, this one is actually the biggest reason why we use logs in pre-calculus 30 is because if we had x in the exponent position, if we applied the logarithm to both sides of an equation, we could then bring this exponent down as a regular coefficient. That's why we use logs. So if you have log of 5 squared, and that's base 10, that's the common logarithm, that's what your calculator works in. Alright, so if we have a common logarithm of 5 squared, which is 25, that's what you get for an answer. And this is saying that that should be equal to 2 times the log of 5, base 10. And so if we have 2 times the log of 5, there we go, it's the same. So if you have the exponents come down in front, it's the exact same value. So those are the laws of logarithms. There's one more that I think comes up a little bit later, so I'm going to make it number 4 right now. I'm going to tell you all about it right now. But it's the change of base formula. Okay, and that is, let me see, that's this. I got it from memory here. So log of x base b is the same as taking log of x to another base divided by log of b to that other base, which in this case we would use the common logarithm log, base 10. But as long as these are the same bases here, this should work out. And the example would be this. Log of 5 to the power, actually let's do an example. Log of 20 base 5. So log of 20 base 5, and we already calculated that out to be, is that base 5 or base 3? My apologies. Base 3, we calculated that out to be 2.72 already. So let's check this new change of base formula. And so that should be equal to the log of what number would I put up top here? Yeah, 20. And we could just use the common logarithm, which is base 10, which you don't have to write the base then. If there's no base written, that means it's a common logarithm, base 10. Divided by the logarithm of 3. So if you do that on your calculator, every calculator can do that. Then we'll go log 20, close that bracket, divided by log of 3 is, there we go, 2.72. Yes, if your calculator doesn't have a special function where you can input the separate, the base that's other than 10, then this is how you do it, exactly. Yeah. Alright, so those are the laws of logarithms. I'm going to talk a little bit, just real briefly, about graphing exponential functions next. So, anybody have any questions? So let's just take a moment to graph each one of these functions and sketch them all on the same graph, either in your notebook or just on the graphing calculator. Okay. And so what we want to do is we want to just kind of compare the characteristics of each of these graphs. Let's explore them a little bit. So that's y equals 0.5 to the power of x right here. So you see it kind of is decreasing. It's a decreasing function. And then what seems to happen over here? Does it stop here, do you think? Or what happens over here on the right side of the origin? It approaches infinity. Well, the graph itself, if it was approaching infinity, it would be going up here like this. So it's approaching, yeah, 0. Okay, I would say so too. Approaching a horizontal asymptote of y equals 0. Now, does that make sense? I mean, we could certainly test values over here. But let's say x was 10. What would y equals 1/2 to the power of 10 be? That would be 1 over 2 to the power of 10. That's a pretty large number, right? So that's going to be pretty close to 0. So it's not even showing up, it's so close to 0. Okay. All right, well, let's do y equals 2x, if you haven't done that already. So 2 to the power of x. Graph that. Oh, look at that. There you go. It actually looks pretty symmetrical, doesn't it? Okay. Now if we zoom in just a little bit, zoom in, enter, what can we see? Here's our first one, and yeah, it looks like it approaches 0 there. Here's the second one. Yeah, very symmetrical. What y value, what y-intercept do they share appearably? Yeah, let's calculate 0. So 0 is 1 for this function. What about for the other function? Yep, it's 1 as well. All right, so we kind of got that. What would your guesses be if you haven't done this already? What would your guesses be about these ones then? If these ones look the way they do you think there might be some relationship there too? Well, let's sketch that. So these two here look very similar. They have the same y-intercepts as well. And it looks like these graphs are symmetrical. Now what I'm going to do is I'm just going to go ahead and put that 0.5 to the power of x in there and see how it, oh, look at that. A little bit different shape. So it kind of decreases a bit faster, goes through 1, but then doesn't approach the y equals 0 horizontal asymptote quite as quick. So they're all generally the same shape. Oh, and we didn't do this one, I guess. Y equals 1x. Y equals 1 to the power of x. Did anyone else get this? Straight horizontal line? Yeah? Okay, does that make sense? That it's a straight line? And it appears that it's the same as y equals 1? Let's see, does that make sense? What if x was 7? That would be y equals 1 to the power of 7, which would be 1 times 1 times 1 times 1 times 1 times 1 times 1. Still 1, right? So yeah, that makes sense. So this is a horizontal line. It's the same as y equals 1. Okay. Now, let me see here. Oh, okay. Well, let's do this one. What is y equals 2 to the power of x plus 3? What does that one look like? And if you have that already up on your graph, you can just maybe adjust that a little bit. Do I have that one here? No. So I'm going to clear these off. Any guesses on what this would be if you haven't done it already? What do you think's going to happen here? It's going to be moved over to the left 3 units? Okay, could be. Do you remember the transformations from last year? All right. So some kind of moving of this graph. I think I agree. However, I don't know if I agree about which direction it moves there. Uh-oh. Uh-oh. So let's do that y max up a little bit more. Oh, look at this. So it actually moves it up. Yeah, it moves it up 3 units. And notice that this is sort of separate from the plus 3, right? So it's kind of like, remember when we did this, y equals x squared versus y equals x squared plus 3, remember that? It's the same sort of thing. This graph gets moved up 3 units. So it's the same thing. This gets up 3 units. Left and right movement, remember over here, left and right movement was when the change was in with the x right there. So y equals x minus 3 squared. That's when we moved either left or right. Remember, this is a move towards the right 3 units. And so what would that look like with an exponential function, do you think? And go ahead and confirm that with your calculator. So what I'm asking is, let's move this y equals 2x. I want that moved over like this, 3 units to the right. So I almost wrote it out there. I want you guys to find out what is this equation. So go ahead and take a minute to test that out. Okay, so I got mine to move over to the right, and this is what it did. I put the movement here, the horizontal translation, in with the x. So that's where you put it. So if we go back, if we go back to here, you see, remember this one here? This moved the parabola x squared. This moved the parabola 3 spaces to the right. Right? 1, 2, 3. And so you need to have the change in there with the x. So this is y equals 2 the power of x minus 3, and that's all in the exponents spot there. Okay? All right. So that sort of concludes a little bit of review. We're not going to do the log graph right now because we need to focus on some exponential graphs and exponential graphs that are important to calculus. All right. So we're sort of taking a look now at 8.2. Really is where we're at, 8.2. Okay, and it's entitled Derivatives of Exponential Functions.